So at the end of the day, we get this from the upstream. So basically, we have the feature information, which corresponds to something like 140 counters, which are the ones that you are seeing, for each of the minutes within the hour. So for 60 minutes. Now, from this information, we can move to the analysis stage. And in the analysis stage, we need to prepare a little bit the Octave environment. The Octave environment is the open environment in which we can run the MIDA toolbox. Then we show a little bit of the information we have. For instance, this is a set of 10 counters, 10 of our features for the first 5 intervals of time, the first 5 minutes, in which you can see here the timestamps for those 5 intervals and the names for the 10 first columns, so the variables, the features. Each of them has a meaningful sense, so we can interpret them. For instance, the first column corresponds to the number of private IP addresses that are source of one of the traffic flows. So the first interval has 0 private IPs as sources. Okay, so once we have this information at the end, what I have is a matrix of data, 60 rows and 140 columns. What we are going to do is to analyze this matrix with PCA, Principal Component Analysis, and for that we need to select a number of components. This is a typical plot for doing such selection. And in this plot, we find for this kind of changing points. So one component seems to be a good selection in this case. If we select one component, then we can use what we call multivariate statistical network monitoring, which is a combination of 2 statistics, which the D statistic and the Q statistic, which are summaries of the behavior of our observations. Each of these points represent one interval in time, and when you see one point that is really separating from the rest, that is for sure an anomaly. Now we would like to know, okay, this is row 61. I told you before that there were only 60 rows, but actually due to inaccuracies of the NFDAM tool, we always get, if we fix our interval to 1 hour, we always get a little bit more. And this is the reason why we get these 61 observations. Now, I would like to know what is it that makes 61 different to the rest of my observations. And for that, we have a tool that is called OMIDA. OMIDA PCA is run to compare 61 to the rest of my observations in my model. Now, what we see is a comparison bar plot. If the bars go down like this, that means that the value in 61 is much lower. So we can see that 61 has lower values for most of the features of the 140 features that are the counters that represent 61. Now let me go back to the last interval. This guy is going to be 61. And if we open it, you can see that the counters, the amount of elements that we get, is much lower than if we look at any other interval here. So essentially, what my analysis is telling me is that the last interval, 61, has much less traffic than expected, much less traffic than the other intervals. And this is again because only a subset of flows has being recognized as coming later than 1 hour, and 61 is not completely full with traffic. So if we really want to get more detail about what may be happening in that hour, we can get rid of 61 and repeat the analysis again. We reduce the PCA without 61, so this is how we take 61 outside our data. We select again one component. In this case, we have the same selection as before, but it doesn't have to be the case. And now we see a better quality picture, if you like, in which again we find another interval that seems to be separated from the rest, 26. Now we can run again OMIDA in order to determine what is it that makes 26 so special, so anomalous. And now we find a set of features which, unlike before, now they have a higher value than expected. So 26 is presenting more higher counters, than what we will expect from a regular interval of time. We can focus on the main bars, the topmost bars, and we can take a look at the features that we have. So the ports is in the region of register ports, which goes from 1,000 to 49,000. So not much information. It can be actually any port. Both the source port and the destination port belong to that interval. We can also see that there is traffic that is anomalous is connected to the UDP protocol. And this is also not providing a lot of information, but again, this one is telling us that the packages within the traffic, the anomalous traffic, tend to be very small. So what we get is a larger number of packages in the traffic of very low storage, very low volume, and connected to the UDP protocol. Okay, if we would like to validate the result that we have found with our approach, we can actually look at some of those features that were connected to the anomaly according to our PCA model, and take a look on the number, the counter that we have for that feature in all our 60 intervals. So if we do that for the protocol UDP, this is what we get. And you can see that 26 is clearly highlighted as an anomaly, the clearest anomaly in all the intervals. So this is kind of validating what we have found in PCA. Remember that at the end of the day, we have a large matrix of information that is modeling an actually large amount of original data. And what I'm doing now is to validate that what we found was actually the most clear anomaly in the data. We can repeat that for another feature, for instance, this in bytes and bytes low, which is the number of packages with low number of bytes. And again, you can see that 26 is clearly showing a larger number of this type of packages. The last part of the analysis, the last part, is to create a file that we will use in the downstream stage. And this file is actually identifying the anomaly both in time and in the features. So basically, this is what we are gonna try and find in the downstream stage. Okay, let's move to the last stage of the MBDA, which is the downstream stage. And in this stage, we use the input that we generated in the analysis. This is the information of time and features related to the anomaly. And what we are trying to do here is basically to map this information in time and features in the original flow of massive net flow data. So what we found is that out of the total of more than 5 million traffic flows, we found a total of 16,000 in which we can find the 5 features we were searching for, the 5 features connected to the anomaly. So this is the total number of flows in the minute that we had identified, but we can still, with the features, reduce the amount of information we need to inspect. This is the idea of the downstream analysis. These 16K logs or flows are stored in a file that is called the parsing output. And in this, we can actually post-process the parsing output. For instance, with these commands here, we can identify the IP addresses in this output. And we found that almost in all of the flows, there was the same IP address. So probably this IP address is essentially the causing address of the anomaly. And we can actually do more. We can take the hour of traffic that we had before and filter it with the IP address we have found, and we can have summary. And you can see that in the summary, essentially all the flows are also connected to the same origin port, this 5060. And actually, all the flows have, 1/4 of the flows is connected to these different ports. So basically, this is seems to be like a probing activity for a specific service that it could be. This is just a theory, of course, because we don't have the original traffic data, but only the net flows, the flows. Sorry, but it could be probing activity over SIP services. So this is a complete example of the analysis of 1 hour, but we don't have to restrict ourselves to 1 hour. We can actually, if we have a larger infrastructure, we can actually measure any period of time that you are interested in. So I hope you like this video, and don't hesitate to reach us out if you have doubts about this service. Thank you so much.